Hello, calculus friends. Welcome to another episode of Let's Take a Look at Some Things for Calc. I don't know what to say for the introduction of this, but today we're going to be talking about the differential. You covered the differential in Calc 1, but I'm going to assume for all y'all it's been a while. But the differential is just a way to try to measure the change of the value of a function using the derivative. So we're going to be using the derivative as a tool today. So I'm going to draw a picture, or maybe not, of what the differential is doing and then define it for you. And we're going to do some applications with it in one variable, then we're going to move it up to two variables, and then end with doing three. So let's start off by drawing a picture. Just draw the best set of axes that you can, because mine were not straight. I'm going to fix them because I want you to get the idea that this is, the x and y axis. So one variable or in two dimensions as we're used to. So suppose you've got a function running through here. I'll use red for my function. And it's just got some curvature to it because, most functions aren't straight. Let me give it a little steeper curve to make it easier to draw this. There we go. Cool. So the idea is you want to try to measure change near a certain value. So say I'm interested in, I don't know, this x value right here. So you go up and you go to its y value, and it happens to be right here. So there's my y. So how you would do this using Calc 1 ideas is, say you wanted to know what happens as you change the value of x. So maybe you just move up a little bit. So I've drawn mine more exaggerated than what you would actually do this, simply because I want you to be able to see it in the picture. So then this value here would be, I'm going to take x and add a certain amount delta x to it. So I'm trying to estimate what's really happening for looking nearby. So what's happening is I want to estimate what's going to happen if something changes, and calculus is the science of change. So you do your derivative right here and get the, oh no, it's erasing. Oh no, bring that back. The undo button doesn't like me. I'm trying to draw something that's tangential to our current value. There we go. So that's my derivative, which gives me the slope of the tangent line at that point. I should have made this steeper, so this will be a little bit easier to see. So then you ask yourself, what is the change in y from changing x? How does y change as x changes? And the reason you'd be interested in this is because you want to ask yourself, well, what would happen if I change my amount of production? That's the example of the marginal of a production function. Okay, so you'll have something that you want to approximate. Let me change colors into something that's pretty distinct from the rest of those. Green. Hopefully this looks different enough from blue and red. So the idea is I want to know where the red dot lines. That's what I'm trying to approximate. But if you don't actually have the whole curve, you might not have enough information to be able to do that. So what you're going to do is you're going to approximate using what's called a differential. You're going to use the derivative, or how things are changing at that time. So imagine you're somebody who wants to estimate your quarterly profits for the next quarter. You have what you currently have for this quarter, or the value at that point. And then you want to go out to another time unit, so the next quarter. Notice how I'm drawing that green line over. And ask yourself, where do I think this is going to be? So you'll use how things are changing, or how much growth you estimate you're going to have, to figure out where you're going to land. And that's exactly what happens here. So we're going to call this dx when we use the differential, but it's just the same idea as delta x. Notice I'm doing the delta x equal to dx down at the bottom. And then I go up using my derivative, or how things are changing at that time, to do my estimate. So instead I'll call this change dy, because it used the derivative. And that's what a differential actually does. So the differential is dy equals the derivative of f times dx. So how am I changing at that time, or what's my slope, times how far I'm willing to go. So it just figures out where that point lands. And it's used to approximate our delta y, which is just how much has it actually changed if I have the function itself. which that was the part in red. I should have did this in red so you can make that connection. Yeah? How much did it actually rise or change? So what's interesting about this is you're using the derivative as an estimating tool to tell what's happening in the future. You're doing what's called forecasting, which is a little bit different from what we normally do. So we're going to do this in one direction to start off with, and then we're going to do it in multiple directions here in a minute. My mic is not picking up as good as I thought it would be. I'm going to move it for a second. Okay, so we're going to approximate delta y when x changes from 1 to 1.1. So the first thing I want to make note of here is that I know what my delta x is. It's the difference between these two. So my dx or my delta x is going to be 1.1 minus 1 or 0.1. So since I know that, I'm going to use it to do this approximation. So, yay! First up, I need to do my derivative. So my derivative of y is going to be, I'm doing 1 over x, which is just x to the negative first power. So imagine yourself multiplying by the power and then subtracting from it. So I have negative x to the negative 2, or negative 1 over x squared is going to be my value. Sorry, I didn't like how that negative 2 looked. So then my delta y is going to be approximated by dy, and my dy is just my derivative of y times my dx. So I'm going to take my derivative of y and then my dx, which is 0.01, or sorry, 0.1. And I know the value, I'm interested in using it. So you'll always use the base value or the starting point with this. So I'm going to be using 1. That's supposed to be a 1. It looks like a 7. Let me fix that. So 1 squared times 0.1. It's going to just give me negative 0.1. So it looks like as I am moving from 1 to moving from 1 to 1.1, I am decreasing in y by 0.01. So going down, because it's y, which is upsy downsy. Vertical, for those of you who like the more technical terms. So what we can do is, since I know how y is changing or decreasing in that moment, I can look at the actual value of y by putting that value into y and then subtracting the 0.01 to get an approximation for that. And that's exactly what we're going to do in these next questions. We're going to approximate values. So let's take a look at that. I'm going to do this next one. So in particular, you want to pick something you actually can find the value of and can do the approximation of more easily. So usually your calculator, you would pull it out at this moment and be like, okay, I'll do the square root of 0.02. But have you ever wondered, sorry, 4.02, have you ever wondered how your calculator actually calculates that value? Let me show you. So my function I'm going to be interested in here is going to be the square root function. Clearly. Oh, sorry, I'm getting some weird non-palm rejection all of a sudden. Click my pen button again so it recognizes. Sorry about that. And I'm going to be starting out at something I can easily do the root of. So my base value of x is going to be 4. And then my dx, or delta x, is going to be 0.02. So that when I do x plus delta x, the thing I'm going to be approximating, I get 4.02. Hopefully you see what I'm up to with this. So I want to do my dy, because I'm going to use that to do my approximation. So remember, delta y, how much I'm going to change in the y direction, should be approximately dy, which is my f prime of x times my dx. Okay, so I need to do the derivative of f here really quick. So I'm going to think of this f as x to the 1/2. Ooh, I should have left room to do this. Just draw a little line right here and make it fit. This is horrible notation wise. Okay, do an f prime. Actually, I'll do this to make it fit a little easier. So multiply by the exponent, then subtract 1, so I'll get a negative 1/2. So this is 1 over 2 square roots of x. Perfect. So that's what my derivative is. Perfect. All right, so I'm going to be doing my delta y at my base, so my x value is 4. That's where I'm doing this at. So I want to use that base because I can actually do the square root of 4, you know what I mean? Times my dx, which is just 0.02. So here I'll get the square root of 4, which is 2, so 1/4 times 0.02, which happens to come out 0.005. Cool. So that's how much my y has changed. And it's positive. So that tells me in moving from being 4 to 4.02, it's increased by 0.05. So how do you figure out what y is going to actually be? So you're going to say, well, I want to do 4.02. It's going to be approximately f of 4 plus my delta y, how much my y has changed. So what's f of 4? Well, that's the square root of 4, or 2.005. Now what you should do at this moment is actually calculate the square root of 2, or sorry, 2.04, and see how close you are. Not 2, 4.02. Square root. Oh, that's right. I always forget that you have to have like a history to do this too. Aha! It's pretty close, isn't it? Sorry, I didn't mean to hit that. Hopefully you can see this on the standard calculator. Pretty darn close, yeah? Good times. All right, let's do this for another approximation. So if you're wondering, oh, well, how does the calculator make it more accurate? Well, it uses more decimal places than I just did. It goes closer. And we'll see how to do that with Euler's approximation in a minute. Or not in a minute, next section. All right, so I want to do E. I'm going to use a different color because I'm worried it's going to get mixed in with the previous example a little. So I want something close to negative 0.00. So for my function, I am going to choose e to the x. I know I'm going to need its derivative, so I'm going to do the derivative of f, which happens to also be e to the x. Now you could have used e to the negative x for this just as well, but it really doesn't matter. My base point, my x value I'm going to start at is 0, and then for my delta x, or my dx, I'm going to use negative 0.01. So I'm starting at 0 and moving down 0.01 to arrive at negative 0.01. So when you're doing this, you just want to pick a value nearby the thing you need to approximate that you can easily calculate. And 0 is a good value to choose for that. You could have picked 1, and then you would have had to subtract 1.01 to get down to negative 0.01, but you would have been further away if you did that, and that actually makes your approximation worse. So the further you get, the worse it is. So x plus dx, or delta x, is going to be 1 minus, or not 1, I just talked about 1. 0.01, which will give me the required 0.01. Here we go. Now I need my delta y, which is going to be, f prime of my value times my dx, approximately. So that's going to be e to the 0 times negative 0.01, and it's that because my derivative is e to the x, which hopefully you remember anything to the 0 power is 1, so this is just negative 0.01. Good times. So then to figure out my value of f, or what is f of negative 0.01 approximately equal to, well, it's going to be f of 0 plus the delta y value, which will be, well, what's f of 0? Well, anything to the 0 power is 1, so that's e to the 0, because that's what f was back here, plus my delta I just got, negative 0.01. So this is going to be 1 minus 0.01, or as you like it, 0.99. Now, let's see how close that was. So I'm going to bring back up my calculator here. Clear. Oh, and it doesn't have an E on here, so I'm going to have to change my settings for a second. I need the scientific calculator, please. I want to do E. Okay. This is a weird calculator. Can I make this bigger to do it as a function? No. Okay. So we'll do e to the caret 0.01 and make it negative. Ding! Is it close to 0.99? Yes. Is it perfect? No, it's a little bit bigger than that. Yay. When we do Euler's method, you'll see how to get more accurate. Should be fun. Okay, so that was doing it in one direction. So now all we're going to do is change this up by saying, ooh, what if instead of just x, I have x and y? So let z equal f of xy. So I have two directions now, and that I could go in for my variables, which means I need a third direction to account for where I'm going. We've done 3D stuff. And when I look at delta x equal to dx, delta y equal to dy, they are real numbers. The differential rules for things that are non-real or complex are different. So just keep that in mind in case you want to ever do some derivative stuff with some complex numbers. Anyway, the total differential of z, keep writing d, so measuring the total change, if I moved in the x and y direction differently, of z is, we'll call this dz, and it's simply going to be the partial of f in the x direction for that xy value times dx plus the partial in the y direction. Are you shocked? Times the change in y. So if you think about this in the 3D sense, what this looks like is, and I'm going to draw this, and I'm not entirely confident that will make sense, but we'll give it a try. So remember, we have our zxy, and I'm going to draw just a simple shape in this. Let's do it in blue, a little light blue. So say I've got like a curving kind of plane going through this area. What'll happen is you'll have some point you're interested in. Let's say it's right here. And then to do its differential in the x direction, which I'm going to do this way, you would do the slope. Blah, 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 blah. And then in the y direction, you would do the slope. This is going to look weird. Da, 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 da. That did not cross the point. Let's try that again, because it looks like it's sloping this way. And then this is the part that gets weird. So you're like, oh, I'll go this far in delta y, and then I'll see how much my slope has changed, and I'll end up, oh no, wait, that looks bad. Never mind, hold on. I shouldn't have drawn it on the graph. I should have drawn it on here. I'll go this far in delta y, go up here, and see where I land there. And then I'll go this far in delta x, and that will lead me to where they cross, which is up here. And what you're supposed to see from this is that it lies off of the blue pattern, and you can't see that at all. Never mind. This is the worst thing I've ever done. It's hard. Let's see if I can find a digital version of this. It's supposed to be that the red line and the green line, when they combine, end up above the blue stuff. Yeah, I hate myself for having drawn that. Let's do some mathing, because, well, that's what we're here for. Woot woot. It's a little depressing listening to me talk to myself about myself, but that's where we're at right now. So I need the partial derivatives for z with respect to x and z with respect to y. And then I'm going to plug in my base point and my differential to get the differential. Okay, so for x, I'm going to be ignoring y, so I should get 4x cubed minus 3y cubed, and nothing from the y squared, because, well, you'll derive it and get nothing. For the y derivative, you'll get 0 for the first part, minus 3, x times 3y squared. The 2's never want to do showing up. Anyway, plus 2y, and that's all fun and dandy. All right, and now I need my total differential. my dz. So my dz is going to be my z derivative in x evaluated at negative 1 and 2. So 4 times negative 1 cubed minus 3 times the y value, which is 2, cubed times the change in x, which is this value, 0.01, plus, and now I'm going to be using this guy with my x and y value in there. So negative 3 times negative 1 times 3 times 2 squared. I should have used square brackets. There's too many parentheses. Plus 2 times 2. And then my differential in the y direction, 0.02. It just seems like I'm doing number kung fu now. This is a disaster. Yep. So let's see. That'll be negative 1, so that's a negative 4. 2 cubed will give me an 8 times 3 will give me a negative 24. Can't believe those are both negative. Oh, that wasn't negative. Oh, but it became negative. Times 0.01 plus, here's where I gotta be careful. So I have a lot of 3's. That's a 9. This is a 4. Negative, negative, positive. When the smoke clears, I should get 36 off that because it's just 9 times 4. Plus 4 times 0.02. I suggest you clean it up like this before you go on to the next step. Anyway, so I'll add these, multiply by 0.01, add these, multiply by 0.01, and here you go. This is what I got. So hopefully you got the same thing when you calculate this. Woohoo! So what does this approximate? It is the approximate difference, between z of negative 1, 2 and z, and so I'm just going to take 0.01 and add it to 1, which gives you negative 0.9, and then 0.02 and then add it to 0.2, so 2.02. So clearly if I wanted to estimate what this was, I just need to add this to the other side. Well, I should probably rearrange the subtraction here to make sure I don't get the negative, but that's what we're up to. Yay! So if I move a little bit in x and I move a little bit in y away from an original point, how much did it change? So this by about a half. Let's do another one. Usually this isn't too bad if you've been really practicing your partials. Ooh, one with a logarithm. This looks like fun. I'm worried I'm going to run out of space, so I'm going to do it up here. So let's see. The x derivative. This is gross. Oh, because it's natural log 1 over the stuff times the derivative of stuff, which, like, x is going to derive and get 1, so I'll just get y cubed. So when the smoke clears on simplifying this, you'll end up with just 1 over x. That's actually kind of nice. Let's do it for y and see if the same thing happens. P.S. it won't. Well, we'll get some things that destroy. As always, the derivative of natural log of something is just the natural log, is just 1 over that something, times the derivative of xy cubed with respect to y. So the x just is going to hang out, and then we'll derive y cubed and get 3y squared. So what will we lose for this one? We'll lose the x's, and we'll lose 2 of the y's. So we'll end up with 3 over y with this. That one's interesting. Okay. Alright. I like it. Let's go ahead and calculate our differential now. So dz for us is going to be 1 over x dx plus 3 over y dy. I wrote this kind of weird this time. I didn't write that last time. Oh well. So I know my value of x is 5, so I'll have 1 over 5 times negative 0.02, and then plus 3 over the value of y, which is 2, times the dy, which is 0.01. So at this point, you should pull out your calculator and calculate this. And when you do that, you get 0.011. So just so we're keeping on the same page as to what this is approximating, this is the approximate difference between z of 5, 2 minus, I'm going to write the minus down here because I'm worried this is not going to fit, z of, so I'm changing x by 0.02, so 4.98, comma, and then I'm going to add to the dy by 0.01, so 2.01. I like doing 2.01. I've done that one twice now, I think. Yeah. Okay. Cool. Let's do some 2D versions of this, like what we were doing with the approximation of the square roots. So I've got this more complicated function coming up here. Ooh, I should have left more space to do this one by like a lot. We'll see how I do. Maybe I can write smaller and make it work. Hopefully you recognize the function being done here is going to be the square root of x squared plus y squared, or the half circle if you rather, depending on, what you remember. And looking at my values, my x is 5, my dx is going to be 0.02, and then for my y I'm going to be using 12, and the dy for that will be, I'm going down by 3 from 12, so minus 0.03. Remember, you're looking for the whole number that's closest if you're really confused about where I'm getting these from. So 11 is just shy of 12. It's like 0.3 below it, so that's why I'm going to use 12 and negative 0.03. 5.02 is just a little bit bigger than 5, so that's what I'm choosing. Alrighty. So when you look at what delta z would be, it would be the square root of 5 squared minus 12 squared minus the square root of 5.02 squared plus 11 point, that's not a minus, it's plus 97 squared. So I'm approximating this value. This, if you do it, you're just going to get 13 because it's one of those perfect trinomials. All right. So first up, I'm going to have to do some deriving. And it's gonna be a fun time. So I need my fx. So I'm going to derive with respect to x. So remember, square root function, we're going to think of this as a 1/2. So I'll move the power out front and subtract from the power times the derivative of the inside part. Now when you're deriving the x squared times y squared, the derivative of y squared is going to be nothing, so we're just going to get a 2x. And hopefully you see by parity, because these are going to be the exact same thing, it's just, you're switching x and y. This fy is going to be 1/2 x squared plus y squared to the negative 1/2 times 2y. Now, I'm hoping you notice that, 1/2 and 2, those are going to cancel nicely. So I'll just have y over the square root of x squared plus y squared, and similarly over here, y over this x over the square root of x squared plus y squared. And you'll see me do that in a minute when I write the approximation. So delta y, nope, not delta y, it's z. I'm thinking back to one-dimensional. I want to do dz. So I want to use my x derivative, which I have up here, which we just discussed is going to be x over the square root of x squared plus y squared times my dx plus my y over the square root of x squared plus y squared. So just so we're aware, remember fractional powers means that it's a root, so this is the square root. And since it's negative, I'm putting it into the denominator to make it positive, times dy, just in case that part was throwing you off. I'm going to put a line in here so I can make this fit. Okay, so now I got to plug in my x's and my y's and my dy's. So my x, as you remember, is 5. So this is 5 over the square root of 5 squared plus 12 squared times 0.02 plus my y, which was 12, over the square root of 5 squared plus 12 squared times my dy, which was negative 0.03. They have the same denominator, so you can add them fairly nicely, and hopefully you know that the square root of 5 squared plus 12 squared is actually 13. So this is like kind of approximating the square root of 13, in case you were wondering. Anyway, it comes out 12.98, and the actual value of this, of the square root of 13, is 12.9800003 and a bunch of other decimals. So it's pretty close. Pretty darn close with the approximation. I keep fixing this too and then hating how it looks. Sorry about that. All right, same game. So if you have been following along successfully up until this point, what you should do now is pause and ask yourself, what kind of function is she going to write for this one? What's going to be my delta x? What's going to be my delta y? What do I think it's going to be that approximates this? And then when I write what I'm going to do it with, you hopefully will have something that works for you. All right, so I'm going to use f is going to be x e to the y. Now, if you picked your x and y in the different order, it will not matter. What is important though is that you sit down and write out what your x values are going to be. So my x is going to be 5, and then the dx for it is going to be negative 0.01, so that if I subtract 0.01 from 5, I get 4.99, which is accurate. And then for my y, my base point is going to be 0, and the amount I'm going to change by, my dy, is going to be, I move down by 0.03, negative 0.03. I tend to choose y's for odds. That's weird. Okay, so in keeping with what we've been doing, let's do our partials. So this is kind of nice because we're treating e to the y as a constant, so you're just going to get e to the y because when you derive x, you get 1. Fy, I should have did this one first. This one is much easier than the one before it. Regrets. Egrets? No, regrets. Okay. So I'm treating x as a constant, so I'm thinking of this as like 4 times e to the y. I'm going to derive e to the y and get itself. So the x just kind of comes along for the ride as I do this. And that's it. Because it would be treated like a constant out front. So a constant times the derivative is just the derivative of the function times the constant. So then, since I did f for this, I guess I'm doing differential in f, because I didn't do z. Whoops. Oh well, it's not going to be any different. So this is going to be the partial of x, which is ey, times dy, oops, not dy, dx, because I'm doing the partial in x. That's a really common mistake I just made, because this one had y's in it. I thought it had to be dy. Nope, that was the partial of the x derivative back here. And then x e to the y dy, because that's the partial derivative of y. Now I'm going to put in my values, so e to the 0 times negative 0.01 plus x, which is 5, times e to the y, which is 0 also, times dy negative 0.03. Yeah, I should have did this one first. This one's much nicer. So when you calculate that, you get 3.3658. Why do I feel like I'm missing a decimal place? 68409. That's just beautiful. Whew. Now, if you actually find the value of this, so if you take out your calculator and put in 4.99 e to the negative 0.03, you will get 4.843523. And you might ask yourself, well, why on earth would I do this? This isn't even close. You are right, sir and madam, or whoever you are and how you prefer to identify. This is not close. And there's a good reason it's not close. We're using straight lines to approximate something that clearly curves in both directions. So this is a horrible approximation in this case. These two are not even like in a ballpark of each other. I'm actually surprised how bad this is. Like, real bad. Yikes. Wonder if I'm going to double check my calculation to make sure I didn't calculate this wrong. So I have good news. This is not that. It's a 0.016. Yep. Let's do some erasing. We're going to pretend this didn't happen. So you calculate this and you get negative 0.16. All right, so you might ask yourself, okay, how does that help me? Well, remember, this is how much it would change if I moved from 5, 0 to this value. So why don't we do 5, 0? So that would be 5 e to the 0 plus, well, in this case it's negative 0.16, which is just 5 minus 0.16, and that's 4.84. Fun times. How close is that to the actual value though? So what you want to do is you want to ask yourself, is that close to the actual value of 4.99 e to the negative 0.03? Let's find out. And it's not bad. It's this is 4.8425 to da 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 da. So it's only really good to 2 decimal places. Oh, sorry about that. So when you look at this, you might ask yourself, oh, well, 2 decimal places. What if I need 3 decimal places of accuracy? Does this get any better? And the answer is no. But there is a way you can use this using what's called the Euler approximation to get this to be more accurate, which is what we're going to do next. So, things to look forward to next week that hopefully are related and make sense. Okay, so I'm not going to lie, I don't think this is going to fit on this page, but we're going to give it our best shot. I believe in you. Um, so let's see what it looks like for 3 variables. Okay, so I'm hoping that, you have probably guessed what this is. So if W is in terms of 3 variables, x, y, and z, the total differential is dw will be the partial with respect to x times your dx plus the partial with respect to y times your dy plus the partial, with respect to z times dz. However much you're changing in x, y, and z with dy, dx, dz. So as you look at this, I want you to think, well, are we ever going to do anything in 4 dimensions? So I go x, y, z, and then somehow w. Well, you can't picture what's happening with that. Visually speaking, we only can see things that are in 3 dimensions as human beings. However, you can do your 3rd dimension as time. So if you have something that's 3-dimensional and moves over time, this would be a great time that you would actually use this. Or if you actually sell something with 3 or more things in it, like 3 products, you would definitely need this. Okay, so we're going to use this to do this next example that I'm very worried is not going to fit, but we'll do our best, and I believe in us. Let's go back to purple, because that one's fun. So I need to do 3 different derivatives for this. I need to do the x one, the y one, and the z one. I'm going to start off with the x one for this w. Oh boy, and it's a quotient, so I'm going to have to do the quotient rule. We haven't done that in a long time, so, oh no, wait. Nope, I have to do this quotient rule. I was thinking about where is x, where is y. I mean, technically this is a constant and this is a constant, so I could rewrite this into it as a chain rule, but that's probably going to be more trouble than it's worth. Let's get to it. So, low d high, so I'm going to do the derivative of the upper part with respect to x, which is just going to be 0 because there's no x's in z plus 5, minus high, which is z plus 5, times the derivative of the low, which will give me a 2x. Draw the line and square the low. Okay, now I got to do w with respect to y. So we're going to do the same thing. It's going to come out exactly the same, except for it's going to have a 2y there, which is kind of fun. So I'm just going to write what this ends up being. So you end up with negative z plus, sorry, that's a z, 5 times 2y all over x squared plus y squared squared. And then the only one that's going to look different is this dz. So this one I'm going to have to be careful, but they're all going to have the same denominator just because that is the quotient rule. You square the denominator and don't touch it. Okay, so here we go. So low, bottom one, x squared plus y squared. Remember, we're deriving with respect to z, derivative of the higher part, so derivative of z plus 5, which is just going to give you a 1, minus high, which is z plus 5, times the derivative of the low. So I'm doing the derivative of x squared plus y squared with respect to z, and that's going to bring me into a 0. So there we go. That was that. So now I'm going to cheat a little bit. I'm going to evaluate this at negative 1, 1, negative 4, and this at negative 1, 1, negative 4, negative 1, 1, negative 4. So we're going to put in the values here. So this is gone because it's 0. And this is gone because it's 0. So the numerator is pretty easy. Z is negative 4. So negative 4 plus 5, that'll give you a 1 with a negative. And then 2 times x, x is also a negative 1, so that'll be positive 1 overall. And then x squared plus y squared, x is 1. Sorry, negative 1, which when you square will give you positive 1. Y is 1, which you square, it will give you another positive 1. Add them together, you'll get 2. You'll square 2, and you'll get 4. That doesn't look like a 4, and I'm getting all kinds of weird tingly is at the bottom. So what's nice about that is from what we just did, we now know what all the denominators are. They're all a 4. So it's just a matter of what do we figure out the numerator to be. And I've already forgotten what the numerator was, and I'm the one teaching this. So negative 4 is z, plus 5 is 1, and then x is 2. So this is negative 2 times a 1 times a negative 1, so that's just going to be 2. Is it a negative 2 though? I need to do that again. So that's a negative 2, and that's just a 1. So it's positive 2. So that comes out a half. Good times. Let's do the same thing over here. So don't forget that negative out front. Z is negative 4 plus 5 is a 1 times negative 1. So I have a negative 1 minus, or sorry, times 2. So this comes out negative 2. That's interesting that the x and y are opposites of each other. Oh, because this is going to have some parabola shape to it, yeah? Good times. All right. Y and x are both negative 1s. When you square those, you'll get 1s, and then you'll add them together, you get 2. Oh, that's just a 2. Okay, cool. So this is going to be 1/2. Oh, I know why I picked this point. Look how pretty that is. That's some tasty stuff right there. Okay, so what's dw? Well, it's my dx, or sorry, my differential with respect to x, my partial, times my dx plus my y times my dy. Perfect. Negative. Right there. Plus my z, which is a 1/2 times 0.03. Oh my gosh. So let's see. What do we get when we add these all together? I pulled out my calculator, not gonna lie. I got 0.025. Yay. That was that one. I don't know how you feel about that one. I have some thoughts. Let me do another thing with a can, because, you know, I'm going to call this Can Week, because that seems to be what's happening. Ooh, I don't want text. Like, so suppose you have a beverage that's cylindrical in aluminum, and it has a radius of 1.5 inches and a height of 5 inches. Approximate the volume of the aluminum used to construct the can if one of each can is 0.03 thicker. So we're going to make it thicker. So draw your can. This one's long because it's much longer than it is wide. This was 1.5. This was 5. And then we're going to make it thicker. So this is going to increase by 0.03. And here's the thing you have to be careful about. When I look at how the other one's going to increase, it's going to go thicker in each direction. So it's going to go up by 0.03 and 0.03. So if I'm going to use variables for this, I'm going to use r for radius. I didn't want to erase that. Every once in a while it's been doing that. That's weird. And then h for height. So what's fun about this is my dr is only 0.03. But when I look at my dh, I'm actually changing by 0.06 because it's going in 2 directions. Neat, huh? This is the common mistake with this one. So my volume is always pi r squared h because it's a cylinder, and I want to see how much is my volume going to change, aka I want to figure out what is dv approximately going to be. Good times. So to do that, I'm going to do the partial with respect to radius and the partial with respect to height, and use those to approximate my change in volume if my change in thickness is the following. Okay, so for this, I'm going to get pi 2rh. So I'm deriving r, leaving the rest alone. Now I'm going to derive h, leaving the rest alone. Oh boy, was that easy. Done. So what's dv? Well, it's going to be my r derivative times my dr plus my h derivative times my dh. Yeah. Okay, so I'm going to put in the values for that. So I have 2 pi times, what's my radius? 1.5 times my height, which is 5, times my change in r, which is 0.03, except for I didn't write this anywhere near far enough over where this is going to fit. 2, 1.5, 5.03, plus some more pi, 1.5 squared, and then 0.06. Haha, okay. When you calculate that, you get 1.6257741, which is much larger than I thought it was going to be. So if you just make your aluminum a little bit thicker for your volume of your can, as it turns out, you even just with this slight change, but this, when you think about it, makes a lot of sense because it's going to change in every single direction, and you're doing it over quite a large can with its height being so tall. Because 5 inches, 5 inches is probably like a monster can. I bet you that's where I got this measurement from. Yeah, it's quite a bit of more aluminum. Maybe you should rethink your packaging increase. A lot of companies are decreasing packages size to try to save money on wrapping and packaging. For instance, have you noticed that if you buy certain beverages, the bezel in the bottom, the little like arc, has gotten bigger? It has, so that they can put in less product, but the can still looks about the same size. Anyway, let's do a production function. Again, I've mentioned these before. They're really common. They come up a lot in economics. We're going to look at a country that produces two different units. That has production Z based on labor and capital. What we want to do is we're going to look at, if I have currently 20 units of labor and 18 units of capital, approximately how much would this change if an additional unit of labor is provided while capital increases to 16 units? And, I said increases. Well, this says decreases. Yep. So I want to write out what's happening here so we can keep track of this. So my X is 20, but I'm going to have one additional unit of labor, so my dx is going to be increasing by 1. And then my y is currently 18, but I'm going to decrease it down to 16, so my dy is going to actually be 2. So I'm going down by 2, so it's got to be negative. So be careful there. So now I need my z derivatives with respect to x, and then my z derivative with respect to y as well. Okay. So I'm going to derive with respect to x, leaving y alone and treating it as a constant. So I'm going to multiply by the exponent and then subtract 1 from it to get negative 0.2, and then y is to the 0.2 power. So I'm going to change this up and do it as 0.8 times y over x to the 0.02. Except for I added in an extra 0 for no reason. And then I'm going to do dz, or I'm going to do dy, not z. Jeez. I was thinking back to that one where I was doing 3 directions again. All right, so I'm going to be leaving the x alone, deriving y, so I'll end up multiplying by y's exponent, and then subtracting 1 to get negative 0.8. I like it better when I have the 0 there, so it makes it clear where the decimal point is. All right, so that's going to be 0.02 times x over y. So notice the ratio changes there to the 0.8. Cool. Let's use that to make our differentials. So I think the change in production by doing more labor and less capital will be the following. So I'm going to have my zx, so 0.08, times y over x, so 18 over 20 to the 0.2, times my change in x direction, which is just a 1, plus, now I need my my derivative with respect to y. So I've got x, which is 20 over 18, so notice it's the flip side, to the 0.8 power, times my differential with respect to y, which is negative 2. All right, and then you calculate that, and you're like 0.34814,164. Aha. So it appears that overall my production still increases by a little bit. So what's interesting about this is you can ask yourself, as I mess with the amount of labor versus capital, what's going to cause an increase, what's going to cause a decrease. Now that I have this production differential using these two, you can take a look at looking at different values of y and x and seeing, what's going to save me the most money but increase my production the most? So you would use a combination of these two with some different dy's and dx's to ask yourself, what's going to be the most efficient way of doing that? Cool. Or maybe not cool. I think it's cool because it's math, okay? We've already established that. Yep. So that's sort of a not even practical. It's kind of a cool application of what you can use this to do. Hope you've enjoyed it. Remember, you can always rewind and rewatch parts if you got confused, if you have questions. Hopefully, you know how to reach me, just in case you don't. I've plastered my email and phone number everywhere in your syllabus, so I hope to hear from you soon. Bye!